it's the microphone in here, but you can use whatever.
Oh, no, the microphone here is better because I'd like to be able to walk around.
Then let's mute the.
Okay. There's a, oh, you're going to mute me there? The thing I don't, am I coming over the sound system or just talking normally?
You are being recorded. It's
Oh, yeah, I guess I'm also used to some amplification, although it doesn't really matter. I have a big mouth, I have a loud voice, I can deal with that. Okay. Okay, so let's go to. Okay, so exams are here. They've been graded for a while, but in fact, I think the last time I came to class here, I had them in my backpack and never pulled them out. Now it's a little weird here. What's being shown is a Zoom screen rather than my screen. I guess you have to be a Zoom wizard to, because I think I have the mode on Windows is to have the two screens be unified. Although I can check over here in this, that icon will pull up the windows in the corner, the right-hand corner will pull up the windows.
For some reason, this
sharing. Oh, okay, so it's sharing a different. Okay, there it is. Okay. So I'm going to go over, at least quickly, the solutions for the problems on the exam, and I'll try to keep it reasonably short because the next section of the course is going to be on Haskell, and Agnisham, who is a Haskell expert, I'm not, is going to be giving those lectures, and I'd like to give Agnisham as much real estate in terms of class time as possible, so I want to try and keep this brief. Okay, and I go over, actually, let's see, so let's go back to the beginning. So this is literally a copy of the exam with my solutions spliced in. Okay, so let's talk. The first problem wasn't about representing recursive subsets of the natural numbers, was intended to be a semi-gift in the sense that it's an easy problem once you see that the right data representation is to use functions. You just have a Boolean function from natural numbers. And then all of the things that you have to define, all the operations are like one line of code. And so so here's the actual text that I wrote with all the things in glory, but you can see things like member, all you do is apply the function that's representing the recursive set to the input. That's it, returns. If the function's a Boolean, it's returning the right thing. Okay, and so, you know, the thing that's a little bit subtle about this representation, I'm not claiming that it would work for a lot of applications because it could get inefficient, right? Because how do you add elements? Well, you build a new lambda that specifically tests to see if the input is the element in question. Well, now say I add 10,000 elements to my set, okay? I've got a sequence of 10,000 tests built up in my collection of lambdas that I'm using. And now you see here, it's just one lambda, but then it invokes S, which itself is a lambda. And so if you look at the actual control that's going to happen, if you added 10,000 elements, then you ask if something's an element of that set, you're going to have to go through 10,000 tests. Or if you succeed, on average, An average successful test is going to be 5,000 long, right? To go halfway through. Okay, so yeah, it's slick, but you also have to look at costs if you're depending on how you're going to use it. Okay, second question. So, at any rate, this is a very familiar problem. I took this from an inventory of problems I have, and it's called orderings because that's an accurate description, but not one that's commonly used. It's the permutations problem, right? And the problem was designed to be given potentially in the context of remotely administered exams. And I don't know what happens when you do a Google search on orderings, whether you come up with code for this. I suspect, I'm guessing it's a lot harder to find a solution, particularly a one written in Scheme, based on using orderings to search rather than permutations. Okay, and the one thing that I think I suggested here was that it was easier if you define this function mapcat. So the solution I wrote includes mapcat. But I also wrote an alternative solution, although it's kind of a cheat, right? So the way, it's funny because, by the way, if you look up permutations, there are other ways to do it. And when I think about it in terms of the program design concepts that we teach, there's pretty much one obvious way to tackle the problem, right? You do permutations for rest, and then you figure out how do I tweak having gotten permutations for rest to get permutations for the whole thing. And so you have this function insert everywhere. So you called rest, it comes back with a list of numbers, but it's not including the first number on our list. It was just done for rest. And now I have to take first and put it in every possible position in every one of those lists. Okay. So in general, for each list that's in LON coming from the rest, I'm going to produce what? If that list is n elements long, what they're n+1 positions in which to put the extra element. Okay, so I'm going to come back with a list of lists from this, and then I want to splice all those lists of lists together, and that's what mapcat's doing. Mapcat is just applying the function to the elements in a list that it's given, but then it splices together the answers. Okay, if you don't have mapcat, then okay. Oh, come on. I guess it goes a little further. Solution without mapcat. So there's this insert everywhere all list, but if you actually look at it, it's really the same code as mapcat, but it's instantiated, so it's just for this function. Okay? So you can take the idea that the structure of mapcat is in the same structure as insert everywhere and all lists. I've just, instead of taking the function as a parameter, I'm plugging in the function that I'm using. Okay, and the other thing that I'm doing is I'm going ahead and internally doing the recursive call to get all of the permutations of the rest, as opposed to having to do that as an argument and passing it in. Trivial change. Okay. By the way, if somebody has a specific question, please ask. Scalar product. I wanted something that was a little numerical and something that worked on list of numbers. And it's, let's see, is there any way for me to, oh, let's see, I guess up there. So anyway, scalar product's about as easy a function that's not absolutely trivial, like summing a list of numbers. As you can think of, it just does pairwise multiplication. It's two lists of the same length, list of numbers, pairwise multiplies them, and it adds those products together. By the way, I wanted to include this in the homework assignment that was due, midnight last night or whatever. And it turns out to be a complete bust in Java. Every now and then you work in Java and you realize, oh, they made a grievous error. And some of them are huge, like the way they did generics, and some of them are in a narrow application area. The number interface in Java is essentially useless because you get no generic notions of addition, multiplication, and so on. All you do is, and in fact, you don't even get I'm trying to think. I don't even think it supports comparable. Yeah, so because you think about numbers. Pardon? No, it does, but I'm not even sure that number supports comparable. You might check that. I was just looking because I wanted to write a fairly general scalar product. For the generic version, the generic extra credit version, I kind of, so, pardon? Oh, well, the thing is, it's an absolute obscenity that Java doesn't support the right definition of number. It's kind of like the person, it was a bureaucratic decision by a committee that they did with number. They, at some point, added in some stuff where the operations that you take for granted on numbers didn't make any sense anymore. Okay, and so there is no interface that corresponds. You have the notion of number in scheme, and there's all sorts of conversions and everything works out cleanly. There's no comparable thing in Java. The only way I know to do scalar product on numbers, I'd have to do a case split and do a separate implementation for each different form of number for which arithmetic works, ignoring the crazy ones they've added. I think there's some atomic integer and things and so on for which all sorts of bad things happen, okay? And what they should have done is they should have had a nice notion of number, and then if they needed some atomic integer, in addition to that, they'd create a new interface for that and number. They didn't do that. And it's, it's kind of like bonehead simple to have done this right. I mean, and I looked up for there's a bit of discussion, this like, Stack Overflow or something like that. And it's inane. It's kind of like their official explanations that are just stupid. It's typical bureaucratic, bureaucracies will just make up lies and just repeat them over and over again. And you can't get an intelligible response back from them. And that was exactly what you're seeing in terms of explanations from the people on I guess it was probably Sun Microsystems side at the time that this took place. And among corporations out there in the technology world, Sun Microsystems was actually a pretty good player, but much better than most, and yet they're still doing that nonsense. So at any rate, enough of my harangue about the way numbers done in Java. It's just there are a whole collection of things at that level that are done wrong. And unfortunately, I don't know of a language that's mainstream and widely used that doesn't have all that kind of words, because it's sort of decided by popular acclamation at the time, and there's no intelligent discussion that underlined it. And you go back and look at it and you say, how could this decision have been made? Pardon?
So this notion of interfaces, you can look into Rust. Rust calls that traits. And it's basically the same thing as interfaces.
Who you talking?
Rust.
Oh, right. Oh, yeah. Well, traits are an old idea in the sense that it came out of the Smalltalk. And traits are really nice. But at any rate, Rust sucks because it doesn't have inheritance. Okay. No, it does not have real inheritance. It has. If you in the end like type classes in Haskell, you might like Rust, but it does not have actual inheritance. Okay. And I mean, in some sense, what goes on in type classes, you get to separately implement an interface, but you don't actually inherit code. Okay. So, at any rate, but we'll see. I don't think Rust is going to make much headway. I don't think Go is going to make much headway. The one new language out there that I might put a little bit of money on, but now I'm not very confident because the internal people controlling it don't strike me as very sophisticated anymore, and that is Swift. Okay. But the advantage, Rust has this advantage, I think, as well, in that it doesn't rely on does Rust rely on a VM? I mean, there's no reason to have that heavyweight VM underneath. I mean, there are all sorts of interesting things that were explored in Java. We now know how to do them in a much lighter weight way. And so why do we insist on retaining it? I don't know. I think it will die eventually. It's just in the world that I'm now going to say a little bit about from the lecture that I had planned, but I'm going to trim. In the world of programming languages, evolution is really slow, right? Because there's so much need to use legacy code. You have a whole workforce that's trained and developing in a particular language. It has all sorts of flaws. In fact, it may be built on flawed technology. So the standard usage of it is not very sophisticated in terms of being able to develop code quickly that's reliable. But the cost of changing is enormous, right? I thought Scala might be the successor to Java when the project first started. It started in the early noughts. So it's pretty old now. And it had attracted a following, but I think actually it's fading. And anybody wants to talk to me about it, I can tell you it was too ambitious. And it runs on top of the Java virtual machine. I thought it would be a new way to program the Java virtual machine. My impression, although I have not looked at it carefully, is Kotlin may work better. What? Okay, let's get back to the exam. Okay, and so scalar product was a huge disappointment when I looked at it in the context of the assignment you just did. Okay, so at any rate, so the whole thing, I wanted a really simple function that it would be easy to convert to tail recursive form, right? And this happens all the time where the standard structural recursion goes, well, you're associating to the right. It turns out the order of operations, because you keep recurring with pending things to be done, is actually right to left. If you write sum of a list and you do it with structural recursion, it actually sums the numbers from right to left. And so you can instead do, you have to write a help function with an accumulator, and you can manage to do the operations left to right. This works great for an operation that it's associative, so you can change the association, so left to right and right to left give the same answers. By the way, those are the same answers on legal inputs, right? What happens if errors can occur? Then right to left and left to right aren't the same necessarily. Generally, you abort with the error anyways, right? But you could have two errors in your list, one on the left-hand side, one on the right-hand side, and depending on the order in which you're doing the operations. One error wins and aborts the computation, so you get different results. Okay, so let's go on. Okay, so merge. People had a little more trouble with this than I thought they would. Okay, I guess because I sort of take for granted that you can sort of do recursive decomposition that isn't purely structural, because it's something that sort of you have to do in programming generally. You know, we teach you structural recursion, template for structural recursion, because it turns out if you sort of naively approach a problem that way, it works such a large percentage of the time. And then you have to decide if things can be really long, so you end up with really deep stacks, whether you need to do some reworking of the solution, such as using accumulators and having help functions. Okay, but in this case, just wanted the standard decomposition. And by the way, you got to do this in the current assignment, right? And I know, could you believe it? I'm writing the solution code and I'm running my merge sort and it doesn't terminate. And I realize I've got a grievous bug. And it took a little while to track it down, not too long. It turns out it's the same damn mistake I was talking about that you can do in binary sort. When you get down to a singleton list, do you recognize you've got a singleton and not do anything? And if you're trying to do partition and you're down to where one of the lists is empty but the other isn't, and you just try, you can end up recurring infinitely, just keeping doing partition over and over again. I managed to do that. And it doesn't happen when I do it functionally. And it turns out that doing things in visitors, I think maybe obscures what the big picture is, right? You need to be thinking things in the big picture. I looked back at the scheme code for the same thing, and it doesn't just have an empty clause and a cons clause. It has a clause that checks for a list of length 1. Because if I'm partitioning a list of length 1, the partitioning is trivial, right? I'm going to have to return 1/2 as the whole, as that one element, and the other half is empty, okay? But if you let it fall through to the recursion case, you'll end up with the same mistake that I was talking about that happens so often in binary search. And the thing that's so subtle about this, you might say, oh, how could you be so stupid? But it turns out there's a whole approach to proving correctness of imperative programs called horologic. It proves partial correctness. It proves that whenever your program terminates, it did the right thing. It doesn't prove the program terminates. So you can take the version of binary search that does not work, it does not terminate, and you can use horologic on it. You can do this lavish formal proof that it's partially correct. Okay? And generally, when people use Hoare logic, they only do partial correctness. So it's kind of an interesting anomaly. Okay, the next question is one that turned out to be a little harder than I intended. This is where you're doing hand tracing, right? Manual tracing. And it turns out, oh no, I didn't get to the next question. I'm still on the text of the previous one, which required you write all the documentation, a fair amount of code. Okay, and first one did, the problem is if you try and define things like and, where you want short circuit and you've got call by value, you can't do it, okay? So the second one is, okay, well, brute force try and use thunks. If I thunkify everything, it's kind of how I can simulate delayed evaluation, but it's notationally complicated, right? I mean, there's a lot of things blow up. And in fact, I've made a mistake here, right? If you look at ampersand thunk, it needs 2 thunks as inputs. What's my second argument? It's not a thunk. It's a recursive call on what is it? Ampersand thunk list, okay? Should have been wrapped in a thunk, okay? And type checking, if I had, which I don't have at all in Racket, static type checking would have caught this, right? Because I would have declared ampersand thunk as requiring these delayed things, and I'm not passing the delayed argument. At any rate, because of that, this thing blows up, okay? And I'm looking at this and I'm thinking, oh, this is a good illustration of why you need to be able to do manually trace. And how did I find it? I manually traced it. I'm thinking, oh, I wrote the code. I was kind of cavalier about it. And then I'm writing the solution. I'm manually tracing and say, this blows up. And then I look back and say, oh, it's obvious why it blows up because I failed to failed to wrap that one argument in thunk. Okay. And so at any rate, a reasonable number of you, if you faithfully executed the manual tracing, you caught the mistake. And so it blows up on rest of empty. It's kind of interesting because the problem is it's the second argument that's not delayed, and that would make sense, right? How do I get the second argument out? A list is a cons of a first and a rest, and the second argument I failed to thunkify, and so it's a rest operation that blows up. In fact, it blows up pretty quickly in the trace. So here. Okay, so here, it's a little long. One thing, by the way, despite the fact that I jumped up and down a lot in class, I guess I jump up and down too much, so you don't really pay attention when I do jump up and down. The step that was most commonly omitted is when you have a function that's been defined. So it's the name of a function applied to arguments. You have to evaluate that first expression, the head expression in an application, which in the case of where it's just been defined, all its tributes replace the function name by the lambda expression. But that is a step. And you say, well, why is it necessary? Well, you can have a head that does some really interesting computation. In general, it has to be evaluated. Right? I could have the head of an application be an application of compose. And I don't even have the right lambda expression there if I haven't even evaluated the compose yet. And so that evaluation of the head of an application is critical. And this will even happen in Haskell, right? If you have some expression that generates that and it blows up, the whole application blows up. Before you even have looked at the arguments. Okay, so going on. Oh, and then the extra credit question. I found the extra credit question surprising. I think the total point score on the extra credit question may have been larger than the total point score across the class on question 5. Why is that? So the problem 6 is the, I'm not getting where I want to be. Problem 6, you use lazy racket. This dialect that we don't really have an implementation of it because there's a notion of experimental dialect lazy racket that's just wrong. Do the right things. And so I give you the rules and so on and so forth. And there's some people that said, okay, I see, I've got those rules, and they can do the hand evaluation just like they did for problem 5, using a different notion of what a value is and a different rule for cons. And the lambda rule now doesn't require values, right? So at any rate, it turned out that people that were sort of doing loosey-goosey stuff came pretty close to getting the answer, right? Because loosey-goosey, you sort of make the reductions that look reasonable and lead the right way. And I suspect then I sort of realized, oh, that's one reason why people find Haskell programming pretty natural, because Haskell doesn't do any reductions unless it has to get the answer. It's kind of like, it doesn't do anything irrelevant. And if you think about call by value, you evaluate all these arguments in advance, not knowing whether they're going to actually be used in the body of the function. And Haskell says, oh, I'm not going to evaluate any expression until you actually ask for its value. I'm not going to evaluate the expression corresponding to an argument in the function unless you ask to see the value of the argument. It's all based on demand. Okay, and the problem, and people actually had an easier time with part A than they did with 2. And let's see, so it actually takes a fair number of steps to get there. Okay, the second one, where you have strict cons. Okay, so now you have laziness in lambda abstractions, but you don't have it in cons. It blows up very quickly, right? Because if you just look at the list I'm forming there, as soon as I have to form the list, if cons is strict, that means it evaluates its arguments to build a value. It's going to have to evaluate the rest as well as the first, and evaluating the rest then forces the evaluation of 1 divided by 0. Okay, so at any rate, this very quickly blows up. At any rate, that concludes my brief overview of the exam. And come see me in office hours if any of these, any of my glib explanations. Pardon? Yeah, you need to switch to your machine, and you want to do it sitting down.
I will use my laptop's mic. So now we are going to talk about Haskell, but before we start that, I want to pause for a moment and reflect on some of the things that has been like repetitive in this course, which maybe we do not do in other courses. So what would be such things? One thing that comes to my mind is types. Anybody has other suggestions to add to this list? Somebody say something. Well, we write a lot of purpose statements. We instantiate templates. We have this thing called data definitions, where we say that a list is either cons or empty, or sometimes we do other kinds of things, like we say that a directory is either a directory or a file, or we have like union types like that, and we write them in our code. And what else? Does anyone want to add anything to this list? Yeah, I can't think of anything either. So we have these kinds of things. Oh, I have another important point, which is immutability. So in other languages, we write code in the sense that we say that when I am executing this algorithm, I have this counter or this variable, and I change that value to that. But in functional programming, we never write anything like that. So these are some of the things that we have been seeing in this course. I just wanted to highlight them. And for some of this, like the languages that we have did not have express syntax or like language level support. So for example, in Racket, we used to write the types in the comments, but we did not really take the type, like the compiler never really knew about the types. I don't think we are going to be able to do anything about purpose statements. But as for templates, like we had this cond operation and like we used to case split on empty or cons. So instead of that, we will have something called pattern matching. We will get to what that means. And as for data definitions, we will also have interesting syntax for this. And we will also take immutability very seriously. So with that, let's actually get to how we can set up our Haskell environment. So on Saturday, I posted a note on Piazza with some instructions about how to install Stack. Has anybody tried that? Okay, so if you try that and like if it doesn't work for you, let me know. I think it's good to have Stack for this course. And basically you can find this instructions. What I did was if you have a Linux machine or a Mac machine, probably like one of these things will work. On Windows, you can try this, or there is something called Chocolatey. So you could try to install Stack with that. Anyway, let me know in my office hours, or you can post on Piazza. So once you have Stack, I have a link to a repository which was also in that. Also in that note. So let me show you what to do. So right now I will switch to my code editor, and most of this tutorial will be me showing my code editor. So can you read this? People in the back? Okay, great. So this is the Stack project that we have. This is inside this Haskell code folder. And over here, I have some code, and I can just run that by saying stack build. So it didn't do anything because I have already built that. And I can run stack test to run test cases. So I have a function defined over here, which is called GCD of some numbers. And I will explain what this definition means later. But it basically takes the greatest common divisor of several numbers. So inside this test folder over here, I have some tests. So GCD of the singleton list 10 is just 10. And if I have 10, 20, 30, what is the number that divides them? That is 10. So you can download this repository and play with that. And you can run stack test to actually run these tests. So I will open a new file over here and start with the material that I want to talk about today. So over here first, I will, excuse me. So I will start by doing some simple definitions. So let's say I have, I want to define a value X. I will just turn off this code prediction for now. So in Racket, we used to write like that. Like if I wanted to multiply 4 and 5, I would write 20. I would write star 4, 5. But for most of the things, we don't need to do that here. We will just write like that. So on the bottom of the screen, I'm going to open this this REPL environment. So in Racket, you would remember, if you remember, there would be a environment, there would be a window in the bottom in which you could type commands, and you would like get to see the results of that. So I did that is called GHCI in the Haskell environment. So I have saved this as lecture 1, and I'm going to load this saying. Okay. So it says it loaded, and I can print X, and it says X is 20. So one thing we will always do in Haskell is that we are going to annotate everything with types. So here I'm going to say that X is an integer. And then I can reload my program and I can ask what is the type of X. So this is the notation for that. So this colon T is for asking the type, and then I ask the type of X. It's going to tell me it's well, I didn't save it. Instead of int, it says integer. Like they're slightly different, but so. So I can ask the type of X, and it tells me that it's an integer. So in this like module with Haskell, we are going to annotate everything with types. So there are going to be a lot of interesting things about types in Haskell. We will talk about them as we go. So let us do something that we need to do in functional programming and try to define a function. So I will define this function, and this is the way we use to write types, and we are going to write this explicitly this time, and we are going to say that it takes an int and it outputs an int. So if I want to define that, I say double me of X is 2 times X, and we are getting the argument by basically pattern matching. And so let's try to run that. So yeah, and we can again check the type of double me. So there is also lambda notation. So how that works is basically instead of having double me, like defining it like that, we can also so I just put this prime to distinguish that function from the other function. So instead of putting the input on this left hand side, we can also put it on the right hand side. And so this is like lambda, like in. So have you guys used the lambda notation in Racket? Like you would write something like that. Anybody remembers this? Yeah. So instead of writing that, like the shorthand notation in Haskell is this. Okay, that makes sense. So now we are going to do something different, which we do slightly differently in Racket. So I want to define a function foo, and I'm not going to type it right now. So one interesting thing about Haskell is that even if you don't tell it what the type is, it tries to figure out the type by itself. And sometimes, of course, it will not work because the function just might not make sense. For example, if I try to do double me prime of 2, that is fine. But if I try to double me prime of the character A, it says that it expects an int, but we gave it a character. So that's bad. So if we do not give it a type, it will try to figure out what the type is. Like for example, I can delete this type over here. And by the way, this is the comment syntax for Haskell. We have this hyphen notion for like a single line comment. So even if I delete the type of double me prime, that is fine. And then we can still ask what is the type of double me prime, and it will tell me that it takes an integer and gives an integer. So it has tried to figure out what is the type. And again, like it can still complain like based on the type that it has figured out. It knows that it wants an integer and it is seeing something else. So anyway, let's get back to the example I was trying to show. So let's say I have an argument. I have a function with two arguments, foo x, y, and I want to define it as 2x plus y. So let's see what the type Haskell has given to this function foo, and we can try to figure that out by asking what is the type of foo. And it says that, so ignore this name for a moment, but instead of saying it takes a pair of integers, it says it takes an integer and another integer and another integer. So what is going on in here? So if we had to write it in the annotation, I would write it this way. And so let me try to explain what is the meaning of this notation. So instead of, how would we write this in Racket or some other language? We would probably write this as this. And what we have on top, that is called the curried version of foo. And then we can do this. This is also fine, but this is not what Haskell programmers usually do. So let me explain how this curried function works. 1 second. Okay. So let's say that I want to have foo of x comma y to be defined as 2 times x plus y. So how I view this is, if I have the function and I'm going to give this the type int arrow int like that. So imagine I have the function, I have foo of 6. So since it's I'm not saying that it's a function on, so if I have written it this way, it's a function of just one argument. So what foo of 6 does is it takes another argument, and it what does foo of 6 do? It takes another argument called y, and it multiplies 2 times 6, which is 12. Sorry. And just adds that to y. So in this sense, I am not taking two arguments at once, but I am taking x, and then I'm taking x, and then that is producing another function which is foo of x, and this function is taking another argument y, and this is producing 2 times x plus y. So instead of thinking of a function of two arguments, we are going to think of this as a function with one argument which produces another function. So in this style of thinking, notice that higher order functions are going to be everywhere, because every time we think of a function of two arguments, we are going to think of it as a function with which returns another function instead. So, and we can actually use this. So for example, because of like the way we understand these functions, I can actually ask what is the type of foo 6? What should be the type of foo 6? So first of all, the type of foo is int arrow int arrow int. So what should be the type of foo 6? I'm waiting for an answer. You want to say something? Yeah, thank you. So that it's an int to int, and what it does is it basically adds 12 to it. We can check that. it adds 12 to that, and it adds 12 to this. So that's what it does. And so basically when we write like that, this is basically left associative. So the interesting thing is that these arrows, I have not put any brackets over here, but what this means, like even without the brackets, is that they are bracketed like that. And basically, like if I have foo 6 2, then this is bracketed like this. So arrows associate to the right, function application associates to the left. Anyone has any questions about this? Yeah.
Yeah, it's interesting. You know, if you split bracket or scheme in your lambda abstraction,
Yes.
then you have to write things this way. You might say, why is it scheme this way? Well, the syntax messed up now. You wanted to add 2 plus 2.
Yes.
You have to say add 2 and parentheses, put a left parent around that and put another 2. You end up with stacked left parents corresponding to number of arguments.
Yeah.
You have a parent after each argument, which basis that's the notation. If you're making everything explicit, Haskell, its design says, oh, okay, curry functions are what we want.
Yes.
So they have a notational system where you don't need it. Right?
Yeah, I completely agree.
Sort of like you basically get what you would get in scheme with explicit lambdas and a horrible notation. You get it for free in Haskell.
Yeah, the syntax would make it painful if it was not this way. So as we saw, like this is sometimes called partial applications when we like apply foo to one argument instead of both. But essentially there is like, even though I'm calling it partial application, it's nothing but a normal function application really. So yes.
I think the term partial application actually comes prior to languages like Haskell, where you had a notion, any special notation, because you had an in-array function which you only can apply it to the first 2 arguments. And so
yes.
Supporting special notation.
Actually,
doing a partial application, it automatically providing.
Actually, like we wrote this by using this argument, like we pattern matched on X, but we can write this particular function in a different way, which is that we just partially apply the multiplication. And seems to be fine. So let's look at other ways of defining functions. So I have this function called XOR, and the type of XOR is that it takes 2 booleans and it gives me another boolean. And it gives me a boolean if and only if it gives me a boolean if exactly one of the arguments is true. So previously we wrote this kind of functions like that by pattern matching an argument and calling it X, but we don't have to call it X. If we want to pattern match on a specific argument, then we can just call the argument by what it is. So we would define XOR this way. So in a sense, this is like a const statement because we are checking like is X true, is Y true. Actually, we will like have something similar to const statements. In a little bit, I will show you like how else we can write this same thing. So we would define this function this way. Yeah. So another thing is, notice that both of the things below this are false. So we may not want to write this twice. Instead of that, we can put wildcards and just say that these are the things we do not care about. So I can just delete this line and I have this wildcard pattern. And what that means is that this catches anything. I could have given this names, like I could have said X or Y. So in this case, it says if it's true and false, then it's true. If it's false and true, it's true. Otherwise, it's false. And just call the things X and Y. Okay, it's complaining because I have multiple of these declarations. So I can actually enable compiler warnings. Let me see if this is the correct syntax. Actually, never mind. I thought that maybe this is not the correct syntax. So I thought that if this is excuse me. But anyway, if you enable compiler warnings, it would complain that there are variables being bound to this name and we are not using them. But anyway, let's use wildcards. This says that we do not care about what these values are. So let's look at more examples like that. I'm going to define this AND function. And how I would define AND function could be like this. So if I know that the first argument is true, I don't need to check what the second argument is. So I could put a wildcard here, but then well, I do need to check what the second argument is. So if the second argument is false, then the answer is false. If the second argument is true, the answer is true. So if I put a wildcard here, I don't know what the name of the second argument is, or like we have not bound it to a variable. So instead of that, I could put a variable name over here and just say X. So this says that if the first argument matches true, then you can just output X. Similarly, if this is false, I could put Y over here and just then say false, but then I don't really need this. This is perfectly fine. But if I wanted to indicate that this variable is not going to be used, I could just use this wildcard. So this is sometimes a good idea. Imagine that you have a huge block of code over here, and if you want to indicate to someone who is reading the code that this variable is not being used, you put a wildcard. So let's try to write the naive version of the Fibonacci function. So I would define this as int arrow integer. There is a slight difference between these two things. So int is like machine like 64-bit ints or something like that, but integers are unbounded integers. So if I wanted to write the Fibonacci function in the naive way using this pattern matching syntax, I would do this. So here I'm checking whether this is 0 or 1, but if it's n, I'm just calling it n, like that is the name I'm giving it. And I am going to do this. So let's see. Seems to be working. Okay. And so let us continue with this and look at further ways to define functions beyond pattern matching. So I want to define a function called myMax, and I guess I'm calling it myMax because max is already taken. So I have two integers over here, and I'm going to call them m and n. But just pattern matching over here is not sufficient. So I could, because I need to know, I need to do a comparison like that. Like I need to do a comparison like that and see if the result is true or false. So I'm going to do a comparison like this. And then, so this is called a guard. In a sense, conditions in Racket are more similar to guards than pattern matching in Haskell, because this over here is a Boolean. So if you asked empty question mark something in Racket, that would be like putting a Boolean. So that is the version of cond over here is basically guards. And if that guard is satisfied, I output m. And let's let's say that for some reason I want to output the first argument, or I mean, if they are both equal, then it doesn't matter. So in that case, I just say otherwise m. So this is like the else clause in bracket. But by the way, there is this otherwise. This is basically just a alias for true. So no magic there. You could have just written true equal to m because this is like the last. And then we can run this. What? Okay. Yeah. Why is it doing? What? What did you say?
The right answer, that's true.
Oh, oh yeah, both of them are the same, right? Yeah, my gosh. Yeah. So, in Racket we had local definitions. We are going to look at some examples of local definitions like that. So, let's say I have a cylinder and I want to find its area. Then, so let's say that these are floats. And this is, say, the radius of the cylinder, and there is the height. So one way to do this would be to do we have like some kind of let syntax. And so I define the side area to be this. So I think pi is automatic. Yeah, it's like part of the standard library for some reason. And then I can write that. So this is the let syntax. And actually there is yet another way to do local definitions, which is the where syntax. So I can say I just want this, but then I would say where side area is that and top area is that. So one thing to note is that this entire thing is an expression, but you can only use where inside like a function definition. Yes.
I have a question about the semantics of flat. Is it true flat application for left application or is it let star? Can you see the definition of side area and the definition of top area?
Yeah.
The right hand side versus side area.
So I think this is perfectly legal.
That's the recursion, but it should be-
Oh, sorry.
But let's start.
What was the other question?
So the three different notions of let.
Yes.
Let, which is the abbreviation for a language. Let star, which is really nested. In the last.
Yeah.
Right inside the follow.
I think this is let rec, but
That star where on the right hand side of the definitions.
yes, but let rec can have multiple bindings, right?
Or-
Let rec can have multiple bindings.
Yeah.
Yeah. So this is the let rec version. I don't think this would make sense, but it will probably get stuck if I try to do it.
Just doesn't have a license to branch.
Yeah, it gets stuck when I do that, but yeah. So the yet another way to define functions is what are called case expressions. So I had a definition of and like that, but it can also be done like this. And I take two arguments x, y, and then I say case x of, and then if x is true, I output y, otherwise I just output false. So these are called case expressions. And this is also one another way you can define functions. So any question about this, all these like ways of defining functions? I don't think you need to memorize them. I will like upload these lecture notes later today, so you can take a look at that. Any questions about any of this so far? So I will move on and talk about something else. So there is a function defined in Haskell called ID. So ID stands for identity. So this is a very boring function. What it does is it takes an argument and it returns it. So the question I want to ask is, what should be the type of identity? I'm looking for answers from the class. Yes. Yes. Thank you. So one way to type identity would be this, which is okay, but it's not great because why can't it take float or something? So instead of that, we will write it as a arrow a. So this basically like there is an implicit for all over here, which we are not writing. But what this means is that for any type A, we are giving the type A. So notice that this is somewhat different from saying any arrow any. Like you could, let's say if you wanted to say something like object arrow object, where an object is like any kind of object. That is kind of not exactly what it is, because here we are losing the information about what kind of object it was. So this is a little more precise than that. This is more, so this is what is called parametric polymorphism. In the world of Java, this is what is written with the generic. So I think in Java you would write this as uh, 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 in Java you would write this as here. So in Java you would write it like that, not object returning object. So is this the syntax? No, the A goes first.
So word, you got to put that in front of the type declaration. It's the very first thing you bracket.
Anyway, I hope.
Bracket is the very beginning of the definition. Say it's going to be a polymorphic definition of the type.
Okay.
And then the next one is, so then you're going to use any way you want. Well, okay, it's the return type, and it's also the type.
So does this make sense to everyone? Any questions about this? So we are going to use like this kind of types in lots of places. So this is just saying that generally, like when we do not know what type this A is, but the type that we are getting and the type that we are going to return is the same. So, okay, let's look at some more examples. Yes.
Case sensitive, does Haskell know?
Kinda, because if it is capital A, then capital A is supposed to be a concrete type. Capital A is supposed to be a concrete type. Like it is not implement.
The actual names and types, those type variables.
Yeah.
The actual typing you get with tabs.
Yeah, we can do this. Yeah, but if it starts with a capital letter, Haskell thinks that it's okay, type is a keyword, but
That's as good as using A.
Yeah, but if I do capital T, then it thinks that it is an actual
Oh,
type.
the type, yes.
Yeah.
So it's case sensitive in terms of what polymorphism.
Yeah, there are like a few other rules like that. So there is another function. Let's do some more of these examples. So I want to write a function called apply, and apply takes a function if and an argument x, and it applies if on x. So what should be the type of apply? Again, I'm looking for answers from the audience. Sorry? The return type of if. Yes, mostly yes. So the type of apply, the return type of apply is the return type of if. So, and what should be the type of the whole thing then? So let's call that return type of if. Let's call that B actually, because why not? So, and any ideas how we should type the rest of the things? Maybe I should like just show some examples first. So first we are going to give some type to the function, and we are going to, should we give the function this type? Probably not, because we don't want to restrict ourselves to the case where the function takes and gives us the same argument, same type. So we would rather call the function's type a arrow b. So a is something, b is something, they are not necessarily related. So this is the type of if. Actually, I can do this multi-line, I think. So I can say type of if, and then I want to put something over here which is the type of x, and then the answer, like one of you said, would be b, because that is the return type of if. So what should I expect the type of x to be? A, right? Because if I am assuming that if is going to take in the type a arrow b, then we must supply it the type. So before we can check that whether the compiler accepts this, and it does. Actually, we could have like not, 1 second. We could have not provided that, and we could have just asked the compiler what this type is, and it would have given the same thing. In different variables, but yes.
Can I ask an obvious question? So that line comments, this is a bit Aaron's question, looks like minus.
Yeah.
It's almost like slash comments or something like that.
Yeah. It's because like sometimes you have this equations in books, and yeah,
Like you start with a fresh.
I think it's sometimes you have equations in books, and like they do a thing and then they write one. I think it's derived from that. Yeah. And so okay, let's think about another example. So let's say I have two functions f and g. How can I define their composition? So does anyone know what composition of two functions means?
Assuming they're unary, was everything's furry, so.
Yes. Yes, I agree. Like there are some catches here. Does anyone know what composition of two functions are? So the composition of two functions is basically like you apply one function after the other, and actually it's like written in backward notation. It's just because it's tradition. What I mean is that I'm applying g first and then if. So it's like, it basically looks like g is happening first and then if is happening. So but it's like written the other way anyways. And instead of putting this thing over here, I could have put this thing over here, and it is the same thing. Both of them are equivalent. So anyone wants to try to figure out what the type of this should be? Actually, maybe we can try to make it a little bit easier. So we want the type of if, then we want the type of g, and then what? So what type should we give to F? Yeah, okay. So let's give G the type A arrow B. Yeah. Yes. Yes. I heard from the audience B arrow C. So, and okay, what is the return type now? Yeah. So the ultimate return type would be C, that is true. But then we want to take in another argument first, right? So we could either write this entire thing as A arrow C. This is fine. We can also remove these brackets, like, because by default the brackets are to the right. So by the way, these brackets don't matter. The last one don't matter, but these brackets do, because if I didn't write B arrow C in the bracket, it would think that it is taking an argument, like taking a value of B, taking a value of C, not a function. So these brackets are important. Like the last one is not really. So yeah, so this is called compose. So actually these functions apply and compose, these are so useful in Haskell or really any functional language. Like they have a shorthand. So compose apply is given this this shorthand, this $sign. So let's say I want to apply fib to 10, I could write that, which is the same as this. So one thing someone might ask is that what is the purpose of having this dollar notation in the first place? The answer is that like the dollar notation is parsed in a slightly different way. So imagine I had fib 10 and I want to use, say, this function double me over here. So I would write it like this. But then let's say that I want to pass that to some other function again. Like let's say I want to add 10 to that. So that's a lot of brackets. What? Let me just ignore that for a moment.
How do you get a plus 10?
So plus 10 is like partially applied plus 10. Like it basically means like 10 plus something. I don't know if I can write it like that. Probably not. But yeah, okay. So anyway, but what I was trying to say is that this is a lot of brackets. Instead of that, one can write it like this. So this dollar is like parsed differently. Like it's parsed to the right. So if you don't want to put a lot of right hand brackets, like then you can just do this. And compose is also very yes. So what dollar does, dollar is, remember apply. So dollar is basically apply. So imagine I have double me fib 10. That is the same as putting a bracket here. So it's just like a parsing magic, like nothing more than that. Is that okay? So the other thing that is, I think we are over time. Okay. I will see you guys on Thursday. Thank you for coming, and try to install Stack and let me know what happens.
For stack build. Dot star stack build.
Next, what?
Install a whole lot.